kids. Do you know the differential dinosaur back talking to you about Newton's law of cooling? I got a question. What kind of dinosaur writes the best essays? A thesaurus!
First thing we're talking about is Newton's law of cooling. This says the rate of cooling is proportional to the difference between the temperature of the object and the surrounding temperature. In other words, this differential equation right here, where this would represent our rate of change or rate of cooling in this case, is means equals, proportional to means K, some constant, times the quantity. And it would be the difference between the temperature of the object at some time t and your surrounding temperature. Now, this differential equation is used to determine the rate at which some object is cooling at a specific time, but it's far more broadly applicable than that, and we'll show you that today. One such application of Newton's law of cooling would be the temperature after a certain time formula. So that would be just the general solution of this given differential equation. So if we were to solve this differential equation, we would end up with a formula that allows us to find the temperature of the object after a certain amount of time. So let's apply our steps that we know in solving a differential equation to this differential equation to get our general solution. So what is the first step in solving a differential equation? That would be to separate the variables. Remember, if you do not separate the variables on the AP test, you cannot get any credit for that question. It's the most important step. In this particular differential equation, it's important to note that capital T and lowercase t are two separate variables. The capital T represents temperature, whereas the lowercase t represents time. Those are the two variables we need to separate. K is just a constant, so it actually doesn't matter what side it goes on. We usually keep it with our independent variable, so in this case, we'll keep it with the lowercase t. So let's separate these variables. This lowercase t, we need to get to the other side, so we're going to multiply both sides of this equation by dt. So now these over here cancel each other out, and we have all of our lowercase t's, well, really only this one on this side of the problem. Technically, we do have another lowercase t right here, but this variable corresponds with the temperature of the object at a given time. So it corresponds with the capital T's, not the lowercase t's. So I need to get both of these capital T's to the other side of this equation. How do I do that? Well, I can either divide both sides by t sub t minus t sub s, or multiply both sides by 1 over t sub t minus t sub s. Either way, these cancel each other out over here, and on this side, we now have all of our capital T's, our temperatures. So now we have successfully separated our variables. Again, K can go on either side, but we usually keep it with our independent variable, our lowercase t. Now I can move on to the next step of solving a differential equation, which is to prepare both sides for integration. So I'm going to integrate both sides. This side is very easy to prepare for integration. This is a constant multiplied to our function, so I can take this constant, move it out front of the integral sign. But on this side, it's a little more complicated. I need to use u substitution, where I set u equal to this denominator right here. That means if I were to take the derivative of each side with respect to capital T, I would get du dt is equal to 1 over here. And then when I multiply both sides by dt, I just get du is equal to dt. Now I substitute u and du in for this integral right here, and I can rewrite it as the integral of 1 over u du is equal to k times the integral of dt. Now I'm ready to integrate both sides and add c. On this side, when I integrate, I just get ln, the natural log of the absolute value of u plus c. On this side, I get k times the quantity, t plus c. I distribute the k to the t and to the c, but remember, k is a constant, c is a constant, so a constant times a constant is equal to a constant. Over here, my c I can subtract to the other side, and a constant minus a constant is still a constant, so I get something that looks like this. Now again, the goal of this is to get an equation in terms of temperature and time, so I need to plug back in whatever I set u equal to, which would be t sub t minus t sub s. I plug that back in for u here. Now I need to solve for t sub t, because the whole goal of this was to get the equation of a temperature after a certain time. So we need our equation to be set equal to t sub t, the temperature at a certain time. So how do I solve for this? Well, I need to get rid of this ln, so I'm going to take the e of both sides, and I do that because over here, the e and the ln, those are just going to cancel each other out, and on this side, we have e to the kt plus c now. Now, this next step is usually the hardest step because it's a little bit confusing, but it makes sense in terms of the properties of exponents. If you multiply like bases, you add the exponents. So if we have e to the kt plus c, we could actually rewrite that as e to the c times e to the kt, because if you multiply like bases, you add the exponents. So this is just going the other direction. Now, we could drop these absolute value over here by putting a plus or minus on the other side. And we've already said that plus or minus e to the c, that's just plus or minus a constant to a constant. So a constant to a constant is still a constant, so we can rewrite that as capital C, and we know that plus or minus a constant is still going to be a constant. So this whole thing can be rewritten as a constant, because that's what it is. We can now solve for t sub t by adding t sub s to both sides, and we now have an equation set equal to t sub t, the temperature at a certain time. That's the formula we were looking looking for. So step 4 in solving a differential equation is to always check to see if there was an initial condition provided. There was not here. So this is going to be our formula for finding the temperature of an object after a certain time. However, we can actually make this more specific if we wanted to. Remember, when we're dealing with proportional rates of change like we are here, in the general solution, your C value represents the initial value. So we can actually rewrite our C in terms of T if we plug in 0 for T to get our initial value. We can now simplify this. K times 0 is going to be 0. E to the 0 is going to be 1. So we just have T sub 0 is equal to T sub S plus C. To get C by itself, I would just subtract T sub S from both sides, and I get that my constant of integration is actually equal to my initial temperature, T sub 0, minus the surrounding temperature, T sub S. So I can take this difference and plug it in for C, my constant of integration up here, and I get my exact formula for finding the temperature of an object after a certain time, where T of T is the temperature of the object after a certain time, T sub S is going to be the surrounding temperature, T sub 0 is the initial temperature of the object, K is a constant, and T would be time.
What do you call blind dinosaurs, dog? Do you think he saw us Rex? Tip time.
Now example 1 says in 10 minutes an object cools from 100 degrees Fahrenheit to 90 degrees Fahrenheit in a room whose temperature is kept at a constant 60 degrees Fahrenheit. How much longer will it take for the temperature of the object to decrease to 80 degrees Fahrenheit? So because we have an object cooling over a certain time, we can safely assume that this is a Newton's law of cooling problem. So we're going to let capital T of T represent the temperature in degrees Fahrenheit of the object at time lowercase t. We know Newton's law of cooling is this differential equation right here, and we have just solved this to get the general solution or the formula that gives you the temperature after a certain time. Now this is what we're going to use in order to solve this question, but there's one thing we need to figure out what K is. So in order to find K, the problem usually gives you an initial condition. Well, yeah, it says in 10 minutes the object cools from 100 degrees Fahrenheit to 90 degrees Fahrenheit, meaning 10, 90 is going to be your initial condition, where 10 is going to be the time that we put in for lowercase t, 90 degrees Fahrenheit is the temperature that we find after that certain time, 100 degrees Fahrenheit is what you're starting at, that would be T sub 0, and then the surrounding temperature would be the temperature of the room, which we see is 60 degrees Fahrenheit. So that's going to go in here and here. So now all we have to do is solve for K. To solve for K, we're going to simplify what's inside these parentheses first. 100 minus 60 we know is 40. Now the biggest mistake that is made in this question would be adding these two numbers together. This is an algebra 1 mistake. You can't add these two together because this number right here is multiplied by e to the 10k. This is not. So we have to solve for K by subtracting 60 from both sides of the equation, then dividing both sides by 40, then getting K out of the exponent by taking the natural log of both sides because we have to cancel out this e. ln of e, those two things cancel each other out, just leaving us with 10k. We can then divide both sides by 10, and we get K is equal to 1/10 times the natural log of 3/4, or approximately negative 0.02877. Notice that K is negative, meaning we have exponential decay here. And that makes sense because the temperature of your object is cooling, so it should be decreasing. Now, one thing I want you to note is that the more you round your K value, the less accurate your answer over here is going to be. So you should technically use this as your K value if you're trying to be as accurate as possible. But you can use this rounded version if necessary. Now, we're not done. We've just found K. So we can take that K value, plug it in our general solution here, and use that in order to actually answer this question, which is how much longer will it take for the temperature of the object to decrease to 80 degrees Fahrenheit. So we're going to take 80, plug that in for T of T over here. We're going to take the surrounding temperature, which is still 60 degrees Fahrenheit. That goes in here and here. The initial temperature still was 100 degrees Fahrenheit. That's going to go in here. And now the only variable remaining would be this T, which represents how much time it would take to go from 100 degrees Fahrenheit to 80 degrees Fahrenheit. So let's solve for that T. How do we do that? Well, we simplify what's inside the parentheses first. Again, you cannot add these together. Please do not make this mistake. You need to subtract the 60 to the other side of the problem, then divide both sides by 40, then take the natural log of both sides to cancel out that e. The natural log of e, those two things cancel each other out. We then solve for T by dividing both sides by this decimal right here. Plugging that in our calculator, we get T is approximately equal to 24.09. Now the question is, what did we just find? We found that it takes about 24 minutes for the object to cool from 100 degrees Fahrenheit to 80 degrees Fahrenheit. But if you read the question closely, it's kind of a trick question. It says how much longer will it take for the temperature of the object to decrease to 80 degrees Fahrenheit? Meaning, we already know it has taken 10 minutes to cool from 100 degrees Fahrenheit to 90 degrees Fahrenheit. We're saying how much longer will it take to go from 90 degrees to 80 degrees? So all you have to do is take that 24 minutes that it took to go from 100 to 80, subtract out that 10 minutes that it took to go from 100 to 90, and you get 14.09 minutes. Meaning, it would take approximately 14.09 minutes longer to cool from 90 degrees to 80 degrees. Now example 2 says you are making a stew. When you take it off the stove, the temperature of the stew is 180 degrees Fahrenheit. The room temperature is 74 degrees Fahrenheit. After 5 minutes, the stew has cooled to 155 degrees Fahrenheit. How long will it take to cool the stew to a serving temperature of 95 degrees Fahrenheit? Now because we have an object cooling over a certain time, I think it's pretty safe to assume that it's a Newton's law of cooling problem, so we're going to let T of T represent the time and temperature in degrees Fahrenheit of the stew at time T. We then know that Newton's law of cooling would be this differential equation right here. We also know that the temperature after a certain time formula would be the general solution to that differential equation. Now this is what we're going to use in order to answer this question. So again, what we want to do in these types of questions is we want to first find K. And the way we find K is by using one of the initial conditions provided. So let's see, was there an initial condition provided? It says the temperature of the stew is 180 degrees Fahrenheit. So that's going to be the initial temperature. The temperature of the room is 74 degrees Fahrenheit. That's going to be the surrounding temperature. Then it says after 5 minutes. Okay, here we go. So 5 comma, and then the stew has cooled to 155 degrees Fahrenheit, meaning our initial condition is going to be 5 comma 155. We can use that in order to find our K. So like we said, the initial temperature is 180 degrees Fahrenheit. That goes in for T sub 0. The temperature of the room is 74 degrees Fahrenheit. That goes in for our surrounding temperature. Our T in this case is going to be 5. That's what we plug in there. And 155 is going to be the temperature of the stew. So now all we have to do is solve for K. So how do we solve for K? We simplify what's inside the parentheses first. Now remember, please do not add these together. This has an E, this does not. So you need to subtract this to the other side of the equation. Divide both sides by 106. Now to cancel out this E, to get the K out of the exponent, we take the natural log of both sides. Now over here, the ln and the E cancel each other out. We can solve for K by dividing both sides by 5. Plug this in your calculator, you get K is approximately equal to negative 0.05380. Again, K is negative, indicating exponential decay. And that makes sense because the temperature object is cooling. It's decreasing. Also note, please don't round K too much. The more you round K, the less accurate your answer over here is going to be when you actually find how long it will take to cool to 95 degrees Fahrenheit. So if you wanted your answer to be as accurate as possible, you would actually use this for your K value. Again, we are not done with this problem. We're trying to find how long it'll take to cool the stew to a serving temperature of 95 degrees Fahrenheit. So we're going to take that 95, plug it in for T of T in our temperature at a certain time formula. We also have just found K, so we can take that and plug it in for K here. We know the surrounding temperature is still 74 degrees Fahrenheit. That's going to go in here and here. The initial temperature we know was 180 degrees Fahrenheit. That goes in here. And now we can solve for T. So how do we solve for T? We simplify what's inside the parentheses first. We then know that we cannot add these two together because this has an E, this does not. So we have to subtract both sides by 74. We then divide both sides by 106. And now we need to get this T out of the exponent. So how do we get T out of the exponent? We have to cancel out the E. So we take the natural log of both sides of this equation. Over here, the ln and E cancel each other out. On this side, we just get ln of 21 over 106. Now to get T all by itself, we divide both sides by this decimal, plug this in our calculator, we get T is approximately equal to 30.09. Now the question is, what did we just find? We found how long it'll take to cool the stew to a serving temperature of 95 degrees Fahrenheit. Notice it doesn't say how much longer in this problem, so we're done. We found our answer. It'll take approximately 30.09 minutes to cool that stew. Now example 3 says crime scene investigators can use Newton's law of cooling to determine the time of death of a body. Suppose that a corpse was discovered in a motel room at midnight and its temperature was 80 degrees Fahrenheit. The temperature of the room is kept at a constant 60 degrees Fahrenheit. 2 hours later, the temperature of the corpse dropped to 75 degrees Fahrenheit. Assuming the average person's body temperature is 98.6 degrees Fahrenheit, find the time of death. So again, we have the temperature of an object dropping over a certain time, meaning it's safe to assume we're going to use Newton's law of cooling. So in Newton's law of cooling, we need to let T of T represent the temperature in degrees Fahrenheit of the body at time T. Now, Newton's law of cooling we know is this differential equation right here, and we also have found the general solution to that, which is the temperature at a certain time formula. Now, in problems like this, we always need to figure out what K is first. And in order to find K, they usually give us some initial condition. So was there an initial condition provided? Well, we know the temperature of the body was 80 degrees Fahrenheit when it was found, so that's going to go in T sub 0. That's our initial temperature. The room is kept at a constant 60 degrees Fahrenheit, so that would be our surrounding temperature. It says 2 hours later. Okay, here we go. So it's going to be 2 comma, and then 2 hours later, the temperature of the corpse was 75 degrees. So 2 comma 75 is going to be our initial condition that we use to find K. So like we said, 2 is going to go in for T, 75 is going to go in for our T of T. The surrounding temperature we know is 60 degrees, and the initial temperature when the body was found was 80 degrees. Perfect. Now we can solve for K. So how do we solve for K? Well, we simplify what's inside the parentheses first. Do not add these two together because this has an E, this does not. So we subtract that 60 to the other side of our problem. We divide both sides by 20. We then get k out of the exponent by taking the natural log of both sides of the equation. Over here, the ln and the e cancel each other out. That's why we did it. We get 2k is equal to ln of 3/4. We then get k all by itself by dividing both sides by 2 or multiplying both sides by 1/2. We then have found k. But if you want to plug this in your calculator, you can get that k is approximately equal to negative 0.14384. Again, k is negative, indicating exponential decay, and that makes sense because the temperature of the body is cooling. It's decreasing over time. Now, we are not done. We just found k. We need to figure out what the time of death was, meaning at what time t was the temperature of the body 98.6 degrees Fahrenheit. So we're going to plug that in for t of t. We're going to plug in the k value that we just found for k, and then everything else stays the same. The surrounding temperature is still going to be 60 degrees Fahrenheit. The temperature when we first found the body was 80 degrees. That goes in there. And now we solve for t. So to solve for t, we simplify what's inside the parentheses first. We then do not add these two together. This has an e, this does not. So we subtract that 60 to the other side, divide both sides by 20. We then have to get t out of the exponent. So we take the natural log of both sides to cancel out this e over here. We then get t all by itself by dividing both sides by that decimal. Plug this in our calculator. We get t is approximately equal to negative 4.5711. So what did we just find? We found that the time of death was approximately 4.5 hours before the body was found. So if we want to determine what time that was, we need to figure out how many minutes is 0.05711 of an hour. So we take that decimal, multiply it by 60, and we get 34 minutes. Meaning the time of death was about 4 hours and 34 minutes before the body was found, and the body was found at midnight. So if we subtract 4 hours and 34 minutes from midnight, we end up getting that the time of death was around 7:26 p.m.
What do you call an ugly dinosaur? An eyesore!
Okay, this says the rate at which a freshly baked cookie cools is proportional to the difference between the temperature of the cookie and the room in which it's being cooled. The temperature of the cookie, G, in degrees Fahrenheit, is always decreasing and fits the differential equation dg dt is equal to negative 1/50 times the quantity, G minus 70. The time T is measured in minutes, and the initial temperature of the cookie is 307 degrees Fahrenheit. So this is an actual AP problem, and we're going to take it one question at a time. Let's start with A. A says, is the cookie cooling faster when it's 307 degrees Fahrenheit or when it's 107 degrees Fahrenheit? So to determine when a cookie is cooling faster, we need to determine the rate at which the cookie is cooling at each of these temperatures. So are we given an equation to determine the rate at which the cookie is cooling? Yeah, that's what this differential equation is right here. So in this differential equation, G represents the temperature of the cookie. So in order to figure out the rate at which the cookie is cooling at each of these temperatures, we need to plug in each of these temperatures for G and see what the rate is. So let's start with 307 degrees Fahrenheit. If I take that, plug it in for G, and I simplify, I end up getting dg dt is equal to negative 6 degrees Fahrenheit per minute. Now let's check what the rate of cooling is at 107 degrees Fahrenheit. So we take that, plug it in for G, we simplify, we end up getting dg dt is equal to negative 2 degrees Fahrenheit per minute, meaning the cookie is clearly cooling at a faster rate at 307 degrees Fahrenheit. Part B says use the line tangent to the graph of G at time t equals 0 to approximate the temperature of the cookie at time t equals 1. So in order to use a tangent line to approximate the temperature at time t equals 1, we need to figure out the equation of that tangent line. So in order to find the equation of a line, we need a point and a slope to plug it into point slope form. Well, let's start with the point, x sub 1 comma y sub 1. Well, we are creating a tangent line. So x sub 1, y sub 1 should be the point of tangency. Well, our line is going to be tangent to the graph at time t equals 0. So 0 is going to be our x sub 1. What's the y sub 1 that corresponds with that? Well, what would be the temperature at time t equals 0? Well, we know that. That's the initial temperature. That's 307 degrees Fahrenheit. So 0 is going to go in for x sub 1. 370 is going to go in for y sub 1. The only thing we don't know now is the slope at that given point. Well, how do we figure out the slope or the rate of change or the rate of cooling in this case at that particular time? Well, we take that point that we just found, 0, 370, and we plug it in to our rate of cooling, that dg dt that we have, where G is going to be our temperature. So we take that 370, that's our temperature, plug that in for G. There is no T over here, so you don't have to plug in 0 anywhere. We then simplify this. 370 minus 70 is 300 times negative 1/50 is going to give you negative 6 degrees Fahrenheit per minute. That's going to be the rate at which your cookie is cooling at time t equals 0 when the temperature is 370 degrees. So we can now use each of these things, our x sub 1, our y sub 1, and our m, our slope, in order to create the equation of the line tangent to this graph G at time t equals 0. So we plug each of those in their respective spot in point slope form. We then can solve this. So so that it's in slope-intercept form by distributing the -6 to the x and to the 0, adding 370 to both sides, and we now have the equation of our tangent line in slope-intercept form. The only issue is this question deals with g's and t's, not y's and x's. So instead of writing y, we're going to write g. Instead of writing x, we're going to write t. And now this would be the equation of our tangent line in slope-intercept form. And we can use this in order to approximate the temperature of the cookie at time t equals 1. So all you have to do is take 1, plug this in our slope-intercept form that we just found for t, simplify, and we end up getting g is equal to 364, meaning the temperature of the cookie at time t equals 1 is approximately 364 degrees Fahrenheit based on our tangent line approximation. Part C says find the second derivative of your function in terms of g. Use the second derivative to determine whether your answer in part B is an over or an under estimate. So let's answer the first part. It says find the second derivative of our given function. Well, we aren't given the function g, but we are given the derivative of our function g. So in order to find the second derivative, you just need to take the derivative of your derivative. And again, we're taking the derivative with respect to time. So what we want to notice is that this -1/50, that's just a constant. We can move out front by the constant multiple rule. We then have a function with multiple terms that we're taking the derivative of. So we want to take the derivative of each term individually. Here, the derivative of g with respect to time. Notice these aren't the same variable. So when you take the derivative of g with respect to time, it's not going to turn into 1. It's going to turn into dg dt. Over here, the derivative of 70, that's just a constant, so that turns into 0. So we end up getting -1/50 times dg dt. Now, normally we could just leave it there, but this question wants it in terms of g. So we're going to take what we know dg dt is, which is this -1/50 times the quantity g minus 70, plug that back in for dg dt, and then simplify these two fractions out front. We now have our second derivative in terms of g. Now the second part of this wants us to use this second derivative to determine whether your answer in B was an over or an under estimate. Well, remember, when dealing with tangent line approximations, we need to figure out, is your function concave up or concave down at that point of tangency? If your function is concave up at that point of tangency, then your tangent line will go under the graph, meaning your approximation will be an underestimate. If your function is concave down at that point of tangency, then your tangent line will go over your graph, meaning your tangent line approximation will be an overestimate. So, looking at this second derivative, we know that 70 is room temperature, and your cookie is always going to be hotter or warmer than room temperature. Because of that, we know that the second derivative is always going to be positive for all g greater than 70, meaning that your function is going to be concave up at that point of tangency at time t equals 0, meaning that your tangent line approximation will be an underestimate because your tangent line will go underneath the graph. Part D says find the particular solution to the differential equation, the same one that was up here, with the initial condition g of 0 is equal to 370. So in order to find the particular solution to a differential equation, we have to solve that differential equation. So the first step in solving a differential equation is separating the variables. It's the most important step. If you don't do this step, you get a 0 for this question on the AP test. So we need to make sure all the t's get to one side, all the g's get to the other side. So this dt needs to move over here. We multiply both sides of the equation by dt. Next, we need to make sure that this g gets to the other side of the equation. So to get this quantity to the other side of the equation, we're going to divide both sides by g minus 70 or multiply both sides by 1 over g minus 70. Either way, you end up getting 1 over g minus 70 dg is equal to -1/50 dt. Now we have all the g's on one side, all the t's on the other side. We have successfully separated our variables, meaning we can move on to the next step, which is to prepare both sides for integration. So we're going to integrate both sides. On this side, we're going to take this constant, -1/50, just move that out front of our integral. And then on this side, you could technically use u substitution, set u equal to your denominator. That means du would equal dg. So you could substitute those in. You would get the integral of 1 over u du. Or you could just recognize that we have a linear function in our denominator down here, meaning if we integrate this, it's just going to be ln of the absolute value of g minus 70. On the other side, we know the integral of dt is going to be t plus c. We distribute that -1/50, and -1/50 times t is -1/50t. -1/50 times a constant is still just a constant, so you can just leave that as c. Now, we want to find the particular solution, meaning we need to solve for g. So how do we get g by itself? Well, we need to get rid of this natural log. So how do we get rid of a natural log? We take the e of both sides of the equation. On this side, the reason we have e to the ln is because those two things cancel each other out, and we just get the absolute value of g minus 70. On this side, we now have e to the -1/50t plus c. Now, this next step is usually the most confusing, but it makes sense in terms of the properties of exponents. If you multiply like bases, you add the exponents. So if we have e to the -1/50t plus c, we could actually rewrite that as e to the negative 1 over 50t times e to the c, because if you multiply like bases, you add the exponents. So this is just going the other direction. I'm going to take that e to the c and move it in front of that e to the negative 1 over 50t, because I want to rewrite this now, since it's just a constant to a constant, that's going to remain a constant. So I can rewrite this as a capital C. And I also want to drop my absolute value bars over here. So it's going to be plus or minus a constant. And since plus or minus a constant is still just a constant, we can just rewrite this plus or minus e to the c in front as capital C. It's just our constant of integration. Now all we have to do to get our general solution is just get g by itself. So we add 70 to both sides, and we now have our general solution. But this one's our particular solution. So what we're going to do is we're going to take our initial condition that they gave us, which is 0, 370. We're going to take 0, plug that in for t, take 370, plug that in for our g. We then solve for c. So 0 times negative 1 over 50 is just 0. E to the 0 is going to be 1. 1 times c is c. We then subtract 70 on both sides. We get c is equal to 300. So we take that 300, plug it in for c in our general solution to get our particular solution. And we're done.